first element is a drive circuit, right? And so this is your input signals. These signals can be analog or digital. Whatever we say, this is the electric uh, input signals. Input signal. It can be analog or digitals. So that is fed into the drive circuit of the sources. Here in Pipeline systems, I told you this the signal is propagating the optical signals, so need some optical sources, right? So here you see some light source would be there. Here light source would be there, and uh, you see these ones. And after the light source, the light will be emitting, but and that light will be coupled into the optical fiber. So to increase the coupling efficiency, generally small fiber pigtail is used, right? That is the fiber. You can say this is fiber fly lead, and after that you need a connector. You need a connector, right? So whole thing is now the transmitter, right? This is the transmitter. A little bit, if you see in details of it's a drive circuit. What is this drive circuit? So if you consider say these sources, it can be semiconductor based optical sources or can be non-semiconductor based materials. Mostly nowadays it is semiconductor based materials, because ultimately this signal will be used to modulate the source. So that's why if you use these semiconductor based materials, either LED or laser diode, then you can easily modulate their output. Of course, for different generations, different sources are there. Say, for example, solid systems, that times sources are not these LED or laser diode, rather they are in the form of high power lasers. It can be solid lasers, like say ND class, in ND class lasers, neodymium lasers, etc. Those are solid lasers are there. Glass lasers, ruby lasers, those lasers are solid lasers are there. So those are high power lasers. So in that case, you need the drive circuit will be different. That times you need external device to modulate their optical source. But in case of these semiconductor-based materials, so it will be either PN junctions, LED or laser diodes, since these are diodes. So basically, PN junctions will be there. So you can modulate. So there will be a drive circuit, a power bias circuit will be there. These are power bias circuit. So you can modulate their output by changing the drive current. So you have to have a drive circuit. It can be analog based. Say, for example, it can be this LED can be in the collector circuit of a transistor. So by varying the by varying, probably you do it in the laboratories. So if you have a LED in the collector side, the proper biasing, other things will be there, right? Then you see by changing the base current of the drive circuit, you can vary the collector current, and accordingly light output will be modulated. So that is one way. But in case of digital signals, it will be modified. It can be MOSFET devices, FET devices. It will be based on FET, right? Switching can be realized. So by changing the drive current of the optical sources in the drive circuit, it can modulate their output. So that's the function of drive circuit. So directly the electric signal is not applied to the source. It is applied to the electrical circuit, like say in the in these regions, in the base emitter regions, your signal is applied, and next it is used to modulate the output of the optical sources. Right. So that is the function of drive circuit. Now, light source, come to the light source. Light source, to some extent mentioned, can be coherent source. It can be incoherent source. So this is the coherent. This is the incoherent source, and this is the coherent source, right? LED, and we'll discuss in details. They will actually the material should be of direct bandgap type materials, so that you can have uh, high efficiency, high power, fast response times, right? And they also, not only this direct bandgap type, but also they must be of DH structure, double heterostructure, DH structure based devices, these light source materials, right? And also there are different configurations are there. Can be say LED. It cannot be a simple LED. It can be it will be say double heterostructures, direct bandgap type materials. Like say it can be NNP type structures. You see NNP, N type, and P type. N capital N means larger band gap, smaller band gap, larger band gap. Right. Interestingly, you'll see it. Probably you have studied. NN can form a junctions in case of hetero junctions. NP form a junction, but NN can also form a junctions, or PP can also form a junctions. Instead of I mean apart from PN, like these things. So these are actually these type of junctions are used in J structures, double structures. Say NNP structure is here, the two junctions are there. Right, that's why it is NN, one junction is there, NP another junction is here. Right. So that's why it is called double heterostructures. So we'll see it in details of this, giving the hints. But you see, these sorts of this type of sources are used in bioptic systems. Right. Next, there'll be fiber fly lead. Actually, this is a small portion of fiber used. This is called fiber fly lead. Right? A small pigtail of the fiber is used to increase the coupling efficiency. Sources are there, but during fabrication, small portion of fiber is inserted so that maximum light can be coupled into the actual fibers. Next, it will be your connector. After that, fibers will be there, right? You see, next will be your fibers. Right. You can see these type fibers are there. Fibers will be there, and this is a connector, or sometimes it is called also coupler. Connector, or coupler. They can be of different types, and this type of connector or coupler would be required at the source end and also at the receiver end. Same type of two connectors are must, because you'll see it when you consider the power budget analysis or lifetime budget analysis. That time you'll see it, power budget analysis particularly. That times you have to you will choose the components, but whether those components can satisfy your link length or repeater spacings or data rate, then you have to evaluate the performance. Right. So in that case, you have to, if it is not mentioned, then you have to assume two connectors, one at the source end and other at the receiver end. Apart from some other connectors may be there, and those may be optionals. So sometimes in between fiber link, there can be another connectors will be there. Also, there can be splices. These are called optical splices or splice. You see, These are optional. So there can be more than one splice to increase the length. There can be more than one splice. There can be more than one connectors depending upon your requirement. Right, depending on the requirement. But these are optionals. Right, but there is certain difference is here between uh, splice. These are optical splices. Optical splice, splicers or splices, of splices, and these are connectors. But these are actually optionals. These are optionals. Maybe there, may not be there. Optional, optional, optional elements. Right, connectors could be there. And next, and the difference is splice and connector is a demountable device. You can connect it or disconnect it as per your requirement in between link or at the source end or the receiver end. But the splice is another type of connecting systems that is used also to joining two fibers together. There can be in a single mode or can be multi-mode. Fiber can be single mode or multi-mode. That can be step index, can be carrier index. But when you use a splice, that means it indicates the permanent connections. Right. When you want to join fibers together permanently, that time splices are used. It can be one fiber, or can be a group of fibers like that. So that times, if you need the joints for permanent connections for permanently to join for if you need the joints permanently, if you want to join the fibers permanently, that times splices are used, or if or connectors or the demountable device. I mean, it can connect or disconnect as per your requirement. And there are different techniques are there. We'll see it. For splices, particularly arc discharge is taking place, or can be using laser pulse, or it can be some mechanical mounts are there, or some elastic tubes are there, adhesives are there. So these are different techniques are there. We'll see it. What the different splicing techniques are there to join the fibers permanently. Right. Next, you see sometimes you have to it needs to split the split the channel into two. So that times you need that time another component used, that is beam splitter or optical coupler. That is also can be optical coupler or can be beam splitter, where you can split the channel into to two or more, right? Like these things. These things, right? So you can have one to two channels. You can have it, right? Like these things, you can have it. So this is couplers. This also you can call it a optical coupler, or beam splitter. right? So you can have one, two, or can be more channels with these beam splitters, right? And next, you see, next in these systems there can be repeaters. In the repeaters, first there will be the first. Okay, repeaters will see it. Here actually receiver and transmitter both will be there. Okay, let us see that configuration in the block diagram forms. So the first component will be optical receiver. This is optical receiver. Receiver. Next will be electronics for amplifications, reshaping, etc. Electronics. I mean here actually optical to electric conversion will be there, and next will be your the optical transmitter. Exactly transmitter we have just now we have seen it. The same transmitter will be there. Optical transmitter. Transmitter. So this is so after that again you need connectors here. And this is your repeaters. This is your repeaters. It is quite obvious why repeater is required for like just like other conversing systems. Suppose if the signal is weak and distorted after certain, generally signal is weak and distort certain distance. So you have to amplify it. You have to amplify it and reshape it. So for that you need repeaters, right, to cover long distance, right? So this is your. So here also in this side there will be a connector will be there. Connectors will be the connectors. Next, repeater. So repeater consists of the receiver, electronics, and transmitter, because there will be this is the signal propagating is optical signals. This optical signal will be converted into electrical signals, and that signal will be amplified and reshaped. After that, again, that signal will be used just like a transmitter you see to modulate the optical sources, and after that you get the light in the optical fiber, launching of light up into optical fibers. So here again, you see after the repeaters, light will be launched into the fibers. And here also there may be splice connectors, etc. as per the requirement. There is splice. Of course, these are optionals. Splice, etc. Those things will be there. Right. This is also splice to connect the fibers permanently. Next, you see, next will be receiver. But before receiver in optical systems, now fiber company systems, now actually one more component is used nowadays. That is, I told you, that is the optical amplifiers. Optical amplifier, right? This optical amplifier, it can be SOA, semiconductor optical amplifier, or it can be EDFA, or it can be PDFA, PDFA, like these things. Erbium doped fiber amplifier, praseodymium doped fiber amplifiers, on NDFA, neodymium doped fiber amplifier, depending on the wavelength used in the systems. So it can be semiconductor-based optical amplifier, or it can be fiber-based optical amplifiers. So optical amplifiers will be there. Sometimes this whole repeater is replaced by the optical amplifiers. There is no need of repeaters in some cases if you use the optical amplifiers. Right. So next will be ultimately will be your receiver. You see, so there's a the first component here will be the connectors. Just the you need connectors. Like in the source side, you need a connector, and next will be your photo detectors. Photo detectors. Basically, they are photodiodes. I'm just going photo detector. Photo detector, and next will be your amplifiers. Amplifier, and next will be your signal restorer. So the whole things actually it is the receiver. So this is actually your receiver. Receiver, and after this you will get your original signals. Your input signal, electrical signal, may be analog or digitals. So same signal you get it after this electrical output signals. Input signals. So optical amplifiers, you see it after this repeaters. That can be splice, can be anywhere. Just showing it here, optionals. But before receiver, generally there is optical amplifier used because after several kilometers, signal will be very weak. So just before photo detectors, amplifiers are used. Of course, optical amplifiers, there are different applications of amplifiers are there. It can be used just after the source, just before the source, or in between the fibers. So accordingly, they can be used as a power amplifier, um, uh, power amplifier, or it could be inline amplifier or pre-amplifier. When these optical amplifiers are used just before the photodetectors, then those are called pre-amplifiers. So it can be power amplifier, it can be pre-amplifiers, it can be inline amplifiers. Instead of repeaters, if it is used, then it is called inline amplifiers. Also, sometimes you see there are different networking. If you just consider, then there will be some splitters will be there, right? So different stations are connected. If different buildings, different offices are connected through optical fibers, if there is just a star coupler like these things, then so before splitting also one booster amplifier is used. So that is also optical amplifier or booster amplifier. So amplifier can be of 4 types. It can be power amplifier if it is just, so sometimes source is source is not emitting light up to that levels. Then after these sources, if you want, you can increase the power by using optical amplifiers, or that is power amplifiers. Or if to increase the distance, instead of, you can replace the repeaters. That times it is called inline amplifiers. Sometimes and also sometimes, and most of the cases, it is used just before the photodetectors to increase the signal to noise ratio. That time it is called pre-amplifiers. Also, if it is in the LAN, then before splitting it is used. That time it is called booster amplifier. Booster amplifier. So these things are there. And the first component you see, first component after this connector you see is the photodetectors. The photodetectors, it can be also on different types. It can be pin photodiode. Then the photodetector means that will convert the light to electricals, right? That can be done in different schemes, using diode, photodiodes, or using photomultipliers, using simple slab of semiconductor that is called photoconductor, pyrotic detectors. Many kinds of photodetectors are possible, right? But in fabric systems, generally they are based on semiconductor-based photodiode. Semiconductor-based materials are used, either PIN or APD. These two are used. PIN photodiode or avalanche photodiode. This PIN photodiode, when is used when the power is moderate, but if the power is very weak, that times you have to use avalanche photodiode. We'll see the exact principles, there are different aspects, design aspects, everything. So we'll see it for detectors. But even if you use the PIN or APD, that current or voltage will be very weak. Right, if micro current can be in the nano ampere to microamperes, so you have to amplify these things. After amplification, then different filtering frequency shaping filters are there, equalizers, etc. Those things will be used so that you can have your original signals, and that will be sent to the destinations. Right. So there's a different elements of almost all the elements are there. Apart from this, some other elements also there that will see it. That can be the fiber bracketings will be there, add drop multiplexer, add drop multiplexers, filters, tunable lasers. So many components are there. So slowly we'll be learning all those things, right? But they are the basic elements required for if you establish the optical fiber link, right? Next, you see, so now we'll focus on the each element in details. So first we'll see in the optical fibers. We'll see different types of fibers, how fibers are fabricated, or the materials are used for fibers, fiber characteristics, fiber parameters, and when you choose, there are different types of fibers will be there, but how to select the fiber. So that for that you have to know the design aspects of the fiber, and you can choose accordingly the sources and detectors depending upon the dimension of the fiber and depending on the characteristics of fibers, right? So now let us see different types of fibers, right? After that we'll we'll focus the sources. Next we'll consider the detectors, and next the other components like amplifiers, and different and system performance, like these things, right? So let us see the types of fiber. Well, fiber, if you see, I told you it's a dielectric in nature, and that guide light from one place to others, right? Of course, other type of fibers also there. In general, if you see any whatever may be the type of fiber, if you see the structure that we have seen it in the previous semesters. Once again, if you see it, there is a core is there, core, right? Surrounding this core, there is another solid layer is here, which is called jacket, and surrounding this, I'm sorry, there is called cladding. Cladding. Around this core, there is another solid layer is there, which is called cladding. This is core. Core is of refractive index. Say if it is N1, and this is cladding. Of refractive index N2, cladding. And surrounding this cladding, also there is another layer is here. So this, you see the three layers are there. Inner solid layer, which is called core, that is a refractive index of N1, and surrounding this core there is another solid layer is here, that is called cladding. Cladding refractive index, it is N2. If it is N1 core, then always N1 should be greater than N2, right? And surrounding this cladding, also there is another layer is here, which is called jacket. A buffer coating is here, plastic coating is here, that is called jacket, or coating is here, buffer coating is here. Now the question is, why it is like these things? Fiber, you see, it is waveguide. It's made of glass or made general plastic, or actually it is dielectric solid. If you see the fiber, it's a dielectric cylinders, solid dielectric cylinders, right? Which will have inner solid cylinders, which is called core. Surrounding these solid cylinders, there is another solid cylinder is here, which is called cladding or refractive index N2. Surrounding this, there is another coating is provided, that is called jacket. Now the question is, why it is like these things? I think it is quite clear. You have seen it also. You know it also to some extent. So this is of higher refractive index. This is a lower refractive index. That is because then only you can have total internal reflections. Of course, that is from the ray optics, but wave optics also will see it. Right. Whatever may be the case, the simplest way to understand the energy, you see, to propagate long distance, you have to have total internal reflections. And in that case, this should be of higher refractive index, denser, then it will be rarer mediums. Denser to the less dense mediums, right? Denser to rarer mediums. So then only total interpretation takes place and you can propagate over a longer distance, right? And in fact, if you see with respect to core, also with respect to air, this can also act as, you can have total reflections, because core is a high refractive index, air is lower refractive index. But you see, contamination will be there, scattering will be there. So to reduce all those things, contaminations, scatterings, etc., then this cladding is used, right? This cladding layer is used, lower refractive index, then the core is used. But still, if they are made of glass, then if you touch it, the dimension is very, very small, so there are microns, so it might break. So to increase the mechanical strength, then on a jacket is buffer coating is here, plastic coating is provided, it's called jacket. Then only it will be flexible fiber, right? Otherwise, if you just touch it, if it is made of glass or micron diameters, then you see it will break. So mechanical strength will be less. So to further increase the mechanical strength, apart from this one cladding, and also reduce, it will reduce not only this increase the mechanical strength, but also it will reduce scattering, contamination, etc. Right. So this jacket is provided. So this is the fiber structure. Now with this, see overall if you see the different types of fibers are there. Actually, if you see, the fibers can be active fibers, active fiber. It can be passive fiber, passive fiber. It can be multiple fibers, multiple fiber. It can be conical fibers, conical fiber. It can be ledging fiber, ledging fiber. Some other advanced type of fibers also there. DSF fiber, dispersion shifted fibers, and polarization maintaining fibers, Panda fibers, polarization maintaining and absorption reducing fiber, Panda fibers, Panda fiber. Also some latest fiber also there, like PCA fiber, photonic crystal fibers, PCA fibers, or holy fibers, or photonic band gap fibers. So apart from this, some other fiber also there, will see it. Say 8Fa, 8 fiber and fiber amplifiers, 8Fa, those things are there, right? Now see, what are those things? Active fibers here, generally fiber use, as I mentioned, it can guide light, but active fiber, it can emit light also. But that light may not be coherent. If it is coherent, then it is called ledging fibers. So active fiber, ledging fiber, almost similar type, but in case of ledging fiber, fiber lasers can be developed. I mean, laser devices, their lasers are there, but a fiber can also be used as a laser by proper designing and proper mechanisms. The fiber can be act as a ledging fibers. It can emit laser light, right? But if it is not coherent, then it is active fibers, right? It can emit light with some dopings. Right? Generally, fiber is made of glass, silica. I told you last times, glass silicon oxide is here, but with some doping, it can emit light, or it can emit coherent light. Coherent light, that can, it is called ledging fiber. If it is incoherent light, then it's called active fibers. Passive fiber, which is actually used for communication fibers, that will focus mostly here in this syllabus. Passive fibers. Here, it can guide light from one place to another. Passive fibers. The conventional fibers are generally mostly the passive fibers. Also, fiber can transmit image. Say fiber endoscopy, generally endoscopy is there for medical purpose. That times you see a fiber is inserted through the mouth or through some body parts to get the pictures of abdominal pictures, etc., ulcer treatment, cancer treatment, etc. For those cases, images are being transmitted. Image can be transmitted. So multiple fibers are there for image transmissions. Of course, they can be coherent bundle, incoherent bundle. Those things are there. Anyway, this is for generally for image transmissions. Conical fibers, sometimes the fibers are uniform, the dimension is constant, but it can be like this also, conical in shape, to magnified or demagnified purpose, like these things. If you use a source this side and receiver this side, that will be magnified. Just it reverse, in this case, it will be demagnified. So conical fibers are there. Ledging fibers I mentioned. Dispersion shifted fibers, so that will see how it can be designed. Generally, fiber, it is a high bit rate system is there, but still some mechanisms are there that will reduce the bit rate, or also that will increase the attenuations. So if you maintain the attenuation and dispersion together, then that times it is called dispersion shifted fibers, right? And here attenuation and dispersion both will be minimum in dispersion shifted fibers. That is widely used nowadays. It is 1550 nanometers at the particular wavelengths we can have it. Panda fibers, that is polarization maintaining fibers. When you use the fibers for extremely high bit rate systems, the times polarization dispersion comes into the pictures. That will degrade the bit rate or increase the bit error rate, right? So to reduce that actually polarization should be maintained. But in conventional fiber, polarization is not maintained. Polarization vector, it is a rotating, like this thing, rotating polarization vector within the fibers. But if you do something, if you fabricate the fiber in such a way that your polarization vector almost remains same, then you see you can use it at a very high bit rate systems, polarization maintaining fiber. In that case, we'll see it. Birefringence, this term is important. If you have times, I will discuss it. What is this birefringence? Right? If you maintain the birefringence, low birefringence, high birefringence, etc., then polarization of the light vector can be maintained constant. That is Panda fibers. Another new type of fiber also coming in the market, that is photonic crystal fiber. Here theory will be totally different. Here you have seen this single clad, single core like these things, but here it can be multiple clad, right? And instead of the high refractive index, it can be of airy holes will be there. Within some airy holes will be there, where energy can be well trapped within these holes, right? So these holes can be air-filled holes or can be some other liquid or gas-filled holes. So accordingly, there are two types of fibers are there. Holy fibers, that is called these the photonic band gap fibers. Those fibers are there. The important advantage of this PCA fiber is there. You can change their characteristics, right? But other fibers are fixed. But as per your requirement, you can design the fibers and you can control the fiber parameters, right? With these PCA fibers. It's very costlier fiber. At present, it is not used for communications, but for switching, for sensors, and some other many applications. These short distance, these PCA fibers are used. So they are the different types of fibers. Next, we'll see again fiber overall fibers are there. Now, if you see a particular fiber, that can be classified as depending upon these refractive index profiles. We have seen the refractive index is here, but as per refractive index profile, fiber can be classified into two groups. One is SI fibers, and that is J fiber. Anyway, today this much, next time we'll say it. But anyway, if you have any questions till now, you can please do. And today I'm just stopping it. It is 50 now, more than 50. So if you have any questions, you can ask what I have discussed today.
Sir,
Anybody?
what was that
Yes.
synchronous and asynchronous in fiber, sir?
What is?
The synchronous and asynchronous part you were saying no in fiber.
Synchronous and asynchronous in what context?
Fiber, sir, regarding fiber you were saying no.
Synchronous, asynchronous I have not mentioned. Synchronous term I have not used.
Sorry, sir,
Synchronous term,
coherent.
coherent, coherent and incoherent.
Yes.
Okay, these are actually related to sources, right? Sources. The sources actually is very important questions. Coherent sources, coherent coherence. Actually, if you see the coherence, that is the term is used for sources, right? Um, this coherence, it can be temporal coherence, it can be spatial coherence. What is this one? You see, if you have a source, suppose if you say red light, right? Red light. That means only one wavelength will be there, red wavelength, but actually it is not a single wavelength. It has some spread is there. If it is ideally red, then it will be a delta functions. Single wavelength will be there, but it's not a delta function. Say light from sun, it is 7 colors are there. Forget about that one. If you have a single color light, that is also not a delta function. Some spread is there, right? Some that means some delta lambda is here, some more than one wavelength is here. That means it is partially coherent. If it is highly coherent, if it is coherent, then will be one single wavelength will be there. That times mathematically you can say a sine omega t plus minus theta, like these things, right? Omega t. That times you see omega single frequency is here. Say this omega 2 pi f, na? This single wavelength is here, frequency is here. You see it, then it is coherent. but actually it is that means it will be sinusoidal from minus infinity to plus infinity, right? Then it is coherent. But actually, practical sources, they are not like this. In the practical sources, we are getting truncated sine wave, right? Like these things, right? So this coherence, it can be a temporal coherence, spatial coherence. As I'm giving the examples, say laser light. If you see the laser light goes straight, that is because it has high temporal coherence, high spatial coherence. Temporal coherence means how many wavelengths are present. Spatial coherence means actually it is a multimode device. Suppose a source, it can be considered a number of point sources, right? If it is highly coherent sources, then each point sources, they are correlated. A definite phase correlation will exist. That time it is a coherent source. But if the point sources, they are not correlated, there is no definite phase correlation, then they are called incoherent sources. Normal sources, practical sources, all are incoherent sources. Say LED, tungsten lamp, fluorescent lamp, whatever the sources you have seen, you see light from sun, natural sources, they are all incoherent sources. Incoherent sources, right? To make it coherent, you need some artificial artificial lasers, artificial device would be required. That is called lasers. Lasers are actually coherent sources, right? Artificial sources. Lasers are coherent. Light amplification by stimulated emission of radiations. So by making a specific structure, we can make this source coherent. Coherent means it will have high temporal coherence, it will have high spatial coherence. Means number of modes will be less and number of wavelengths will be less. So actually sources, even the source, laser sources, they are not also perfectly coherent. They are actually quasi monochromatic. You can say quasi, I mean monochromatic. You can say this term is monochromatic. Means single wavelength means monochromatic. That means highly coherent. Many things are there. Anyway, to some extent, when you discuss the sources, these things will be more clear. So sources can be coherent sources, can be incoherent sources. All natural sources, keep in mind, are incoherent sources. Say LED, light emitting diode. They are actually incoherent sources. The a problem with these incoherent sources is that their emission profile is quite large, right? I mean, if you launch light in fibers, a portion of light will be coupled, but the fabrication is very easy. But if a laser source, then their emission profile will be very narrow, like these things. So maximum light can be coupled in an optical fiber. I think basic concept is to some extent clear or not? What is coherent and incoherent? So he's asking.
Yes, sir. Yes, sir. Clear.
We'll discuss in more details when we see the sources, right? Emission profiles, these things, the structures, these things will be discussed. Anyway, today, any other questions? Yes, any other questions that you have doubt? Quickly. Any other?
No, sir.
Okay, then next time we'll see it. Just wait. Just wait. I'm taking your attendance. Just a minute.